So a little bit of advertisement. So if you don't know, well, you probably know the state of São Paulo, but I work at UNESP, which is the State University of São Paulo, or Universidade Estadual Paulista. It's a multi-campus university, so it's spread all over the state of São Paulo. It has, in fact, 34 institutes spread over 22 cities. And we are based in the city of São Paulo. There are only 2 institutes in the city of São Paulo, the Theoretical Physics Institute, where I am, and the Institute of Arts. We're located in a building in Barra Funda. So if you've ever been to São Paulo, Barra Funda is one of the big transport hubs. So there's a train station, a subway station, and a bus, intercity bus station as well. So it's very easy to get to the institute. And I'm telling you this because we are a small institute. It's actually started as a public-private endeavor, and today it's small. It's only about 15 faculty, and in actual fact, historically, it's a high-energy institute. So essentially, I am the only person doing condensed matter physics right here on a permanent basis. But we host a branch of the International Center for Theoretical Physics, which is based in Trieste. And so if you are familiar with theoretical physics, you obviously heard of Trieste, which is a UNESCO institute. And we are the first branch outside of the main campus in Trieste. There are more, one in Mexico, one in China, and one in Africa. And we organize the same way that Trieste organizes a number of activities. We do the same. So every other week there is an activity going on. We have funding to bring students and postdocs and young researchers to take part in any of these activities. So come to our website, check the activities, apply. There are a lot of cool things going on around the years. I don't know if I have to check, but there is going to be a school on machine learning at the end of the year in December. I'm not entirely sure if the applications or deadline has passed, but this is becoming a yearly thing. So probably next year we'll host another school on the same kind of idea of doing machine learning. So if you're interested in machine learning, which is what I'm going to talk about, you should check this out. So this is my advertisement, and I'll move on to actually talking about science. And so the idea is to give you a little bit of a motivation of why we do the things we do. This is especially tailored towards electrochemistry, so this is our ultimate goal. And to understand microscopic structures of, at the end of the day, metal-liquid interfaces, but what I'm going to be talking about today is only the liquid, which is already something that is quite interesting and extremely difficult to understand. And so basically what I'm going to talk to you about is the idea. I mean, we're physicists, and the whole idea is that we like to solve complicated problems, and I'll try to convince you that something as simple as water is actually very complicated, and that we have to, come up with a full machinery to deal with it and try to simulate these kinds of problems. So I'll talk a little bit about how to tackle these kind of problems, show a little bit of the results, and then talk about conclusions and an outlook for what we can do in the future. So basically, what we want to understand is how liquids, and in particular water, interacts with a metallic interface. And there are 2 reasons for that. First of all, because from a macroscopic point of view, we are interested in, or the whole idea of green energy is the idea that you're going to use renewable forms of energy to power, your house or power your car. And one of the forms of energy that you can do is hydrogen, is to obtain hydrogen from water. So to do, or even something even more complicated, you can do reactions that are catalyzed by a surface, a metallic surface, And these reactions are typically done inside a liquid, mostly water. So this is the idea from a kind of a applications point of view. From a basic science point of view, what we would like to understand is that there's a microscopic interaction between the liquid and the surface, and this microscopic interaction is actually quite complicated, and it can lead to some things that are very interesting. For example, if you take a platinum surface and you cut it in different directions, so say for example 100 and 111, then just because you change the orientation of the metal, which is a crystal, you can get a hydrophilic or a hydrophobic surface. So you see, you have even the same material can be either hydrophobic or hydrophilic depending on the orientation of the metal or on the orientation of the material that you're using. So understand, and there's no real kind of microscopic understanding of this type of behavior. And so even from a fundamental point of view, this is quite obviously then you can use this information to, you know, make more hydrophilic or hydrophobic surfaces depending on the type of material and depending on the orientation. So you can tailor your system to be more hydrophobic or hydrophilic. And we would like to understand these things. So this is currently ongoing in our group, but I would like to take a step backwards and look at something you know, slightly simpler in a sense. But continuing in that direction, before we do that, there's another issue that if you're doing electrochemistry, then there's an extra ingredient, which is a battery. And so if there is a battery, it means that there is a potential difference applied to your system. And so between, you know, two electrodes, they're an aqueous solution. And if you apply a battery, then things can reorient, especially water, because it's a polar molecule. Then as you apply an electric field, these water molecules actually might reorient on the surface. And if they reorient on the surface, then they might change the electronic properties around that region and change the chemistry that's going on, the reactions that might go on that surface. So understanding these kind of things is also something that is important. And we actually have some contributions in that direction. We have done some work on doing simulations, atomistic simulations of different kinds of materials, where we take a surface, we put a water molecule, and then we introduce via something called non-equilibrium Green's functions methods, which allow us to calculate systems which are out of equilibrium, simulate these systems which are out of equilibrium, to see what happens to a water molecule. In this case, it was a very simple system, just a water molecule on the surface of a metal. And we see that depending on the bias, we can change the orientation of the water molecule. We can change the vibrational properties of this water molecule. And this is in line with what you see in experimental results. So, but you see, these things are very complex. I mean, this is a huge calculation that you have to do if you want to do a calculation where you put the atoms and the electrons in the right places. So it's a huge system to simulate. And furthermore, you want to do this with an out of equilibrium method. Okay, but if we look just at the liquid, so just water, the water molecule is a deceivingly difficult molecule to calculate, to simulate. This is because if you think about water, you have H2O, two simple atoms, so they're not heavy. You don't have to worry about electron spin orbit interactions. They're covalently bonded. However, when you interact these covalently bonded molecules with other molecules, then this interaction includes a lot of different types of interactions. There's electrostatic interactions, there's van der Waals interactions, there's the formation of hydrogen bonds between the hydrogen and the oxygen. And so what we're saying is that there are strong and weak interactions. So the energy scales is a broad range of energy scales. And the moment you have a broad range of energy scales, then things become difficult because you have to include all these type of energy scales in your simulations. there's an extra ingredient which makes it even more difficult to calculate, and probably you as a student has never looked into this problem, even if you're a condensed matter physicist, is the fact that usually we treat, the nuclei as a point charge in our system, and so we separate, the electronic properties from the nuclear properties, and they propagate on a single energy surface. However, since hydrogen especially is a relatively small atom with just a single proton, then what starts to happen is that the wave function of the proton actually has to be taken into consideration as well in your simulations. So this is what we call nuclear quantum effects. So we need to treat the nuclei as a wave function, a wave packet, instead of just a point charge. This actually has extremely important considerations in proton transfer, for example. So even in systems where the hydrogen moves around between two molecules, this is extremely important. And in water, because it's mostly hydrogen and oxygen, then actually it plays an extremely high role in these systems and the properties of the systems. And this is something that I'll show a little bit at the very end of my talk. Okay, so what we want to do in this kind of systems is I would like to essentially what we need to do is to simulate the problem of finding a very complicated energy surface, right? So if we're looking for the ground state of this system, then we want to minimize, find the minimum of this energy surface. But if you want to do dynamics, then we want to, pass around points in this energy surface depending on the different configurations. Since we have, a huge number of molecules, so if you're treating, a bulk system, we have a huge number of molecules, and they're all disordered, and they move around. So essentially, this energy surface has a lot of minima, and in actual fact, what we want to do is to move around this minimum, around the minima, but over the entire energy surface in principle. So we want to do this, and there are various ways that we have devised over the years to solve this problem. So the simplest possible way is actually to say, okay, the atoms or the ions are little balls, and these little balls or these little points are connected by various types of interactions that we model. So we say, okay, a covalent bond is a little bit like a spring. So it has a squared dependence on the distance. But I can also include, so this is the interaction between the next atom. But then you can have interactions which are bending interactions. So spring interaction as well, but on the angle. So it involves three atoms. You can include torsions. You can include van der Waals interactions, which means that now the atoms are not bonded, but they have some form of model interaction. And if the ions are charged to simulate something like an ionic bonding, then you put also an electrostatic interaction. And in principle, then you set up, this potential that depends right on the relative positions between all these things and relative angles. And the key point here is actually to say, okay, I need to fit somehow these parameters to either some, very complicated, complex quantum mechanical simulation, or I fit these things to experimental results. And this is what we call a classical molecular dynamics. Then what we can do is essentially we have potential, this potential is classical. We evolve this potential using Newton's equations of motion, and essentially everything can be solved for a relatively large system. And so you can evolve in time the movement of these atoms connected by these bonds. The problem here is that, first of all, you're ignoring completely the electrons. The electrons are all included in these parameters, so they're kind of folded into these parameters that we're fitting. It involves some fitting of the parameters. So there's no guarantee that whatever you fit for a certain system will work for another system. And in particular, say for example, you have sp2 carbon, which you have good parameters for, then sp3 carbon doesn't work the same way. They have another set of parameters. So the chemical environment around the same atom will change the parameters of that atom. And so these things become slightly more complicated, meaning that you cannot really, treat a reaction where sp2 carbon goes to sp3 carbon. There are extensions to these methods where, you can simulate reactions, but I'm not really going to talk about that. Another possibility is to go to quantum mechanics. We assume that, the ions are point charges, and then we have a potential of the electron-ion interaction. We have electrons interact, and then in principle we can write down the Hamiltonian for this full system. We know how to do that, and if we know how to solve this problem, this second-order differential equation, we get the wave function of this system with many particles, and we would be done. Now, for a system of many electrons, these things become extremely complicated. So we can only do, what we would call full configuration interaction on a very, very, very small systems. So if you're interested in solid state or even in liquids, then things become extremely complicated to solve using, the full machinery of quantum mechanics that you see usually in an undergraduate or even a graduate course. Now, this little guy here, in the 1960s, 64 and 65, he came up with an alternative way, so a exact but alternative way of solving the problem of many electrons. And the way he does is that he said, okay, let's forget about the wave function, and let's focus on the charge density, which is not a 3n parameter body, but only a 3-parameter function, right? It's a function of r, x, y, and z. And then what he shows is that you can get all the information from a particular physical system just by knowing the charge density. So essentially what you can say is that any observable is a functional of the charge density. And then he devised, in fact, a set of equations, because although you know that there is a functional for the energy or any other observable, you don't know exactly what the functional is, right? But he devised another method which actually makes these things practical, where you map a problem, an n-body interacting problem, into a n non-interacting problems. And so you can write down, and this mapping actually allows us to do the calculations that we do today, right? So essentially what we do from a practical point of view is that you write a Hamiltonian that is an effective one-body Hamiltonian that has terms which are a kinetic energy term, a electrostatic potential term that is basically a classical Coulomb interaction. Then you have the external potential, which is the interaction of the electrons with the ions. And then you have this term which we call exchange and correlation potential, which includes all the information that we don't know about these mapping, right? And then this is a problem. And so the problem of finding the functional actually moves to finding the correct exchange correlation potential. We have to do approximations on this because we don't know what is the exact exchange correlation potential. We start off by doing what we call local density approximation, which is the simplest possible approximation that you can do. Now, it's incredible that even at the level of the LDA, and this is really, you know, why things actually, people started to actually consider this seriously, is that even at the level of LDA, for solids, you get, you know, very good results for the electronic properties of solids. Then later on, things moved where you actually do small generalizations. So you do, instead of doing, you know, a uniform local density, what you do is small changes, gradients of the density. And you can move on this, what we call this Jacob ladder of approximations, where you include now, instead of just the gradient of the density, you include also the Laplacian of the density, and so on and so forth. And you can also include, which is not contained here, for example, in DGA, you can come up from the side and do some extra stuff, like include van der Waals interactions. So you can model van der Waals interactions so that you could actually include this into your GGA, for example. There's an issue if you're a chemist. So if you're working in chemistry, and now even a lot of people in condensed matter physics, if you're doing simulations with these materials, then people have been doing hybrid functionals, which essentially means that you're taking the spirit of density functional theory, but you're including a little bit of corrections coming from Hartree-Fock, which is a wave function approach. So if you're a purist of density functional theory, you might argue that, you know, hybrids are not exactly density functional theory, but anyway, from a practical point of view, they actually improve quite a bit if you're looking, for example, for band gaps. So this is the current situation of you know, calculating the electronic properties of materials. So this thing's actually, so the quantum classical methods actually didn't appear here, but so the idea is that if you want to do, you know, move around atoms, then you have two possibilities. You can use those classical methods, and the upside of those classical methods is you can do very large systems because everything is a kind of point objects that are particles that are moving around by Newton's second law. So it's relatively easy to model, right? Relatively easy to simulate. So you can do, you know, even millions of atoms simulation. So this is very useful, for example, if you're doing bio molecules. And then you have quantum mechanics, and our workhorse has become density functional theory, but there are other wave function based methods as well. The advantage is that electrons are included, so you can simulate electronic reactions, for example, chemical reactions. So it's more precise and includes more information, but the number of atoms that you can actually consider in your system is relatively small, right? Relatively small is that at best maybe 1,000 atoms for a short period of time when you're simulating things. And the other downside is that it's only as good as the exchange and correlation potential that you're using, so that you choose to use. So this is another problem, and we need to tackle this problem. Okay, so the idea is, okay, how can we get the best of both worlds? So how can we simulate the properties or the dynamics of a system where we get the accuracy of density functional theory, but we can tackle very large systems with accuracy, right? The accuracy of the exchange correlation potential that we're using, right? So it can only be as accurate as that. And in actual fact, what I would like the extra ingredient that I would like to do to include is that I don't want to have a model, right? So I would like to have something that is as accurate as possible, but forgo a model. Say, for example, like we built this potential is all these terms which relate to a physical kind of description of the system. Now here, I want to say how black physical intuition from this, but at the same time, I don't really have to, ask myself whether I'm including all the ingredients or not. Right? So that's the advantage of this kind of approach. Okay, so what we want to do essentially is teach a machine to predict for us, given a certain structure, so given the positions of the atoms, where the atoms want to move next, right? So what are the forces on the atoms? So given a certain arrangement of atoms, I want to say, okay, at infinitesimally longer time, what is going to be the position of the atoms? And so this is what we're going to do. We're going to teach a computer how to tell us this, which is basically, what computers are doing. And in essence, what we're doing is trying to teach a computer to distinguish where the atoms there are and where they're planned to be, right? And usually, computer scientists, which are talking about machine learning, which is what we're doing here, usually talking about cats and dogs, and getting a computer to distinguish or learn what is a cat and what is a dog. The key issue here is that we need to make sure that it distinguishes between cat and a dog and doesn't make a mistake about, of something else, right? So it doesn't really blow up to go somewhere else. You really must, stay within our problem. And in mathematical terms, basically what we need to do is we're going to do a regression. So what we want to do is to minimize some function, and you can use various methods to do this. Typically by doing, a gradient descent is and in essence, basically this is a much more complex, but following the same idea as a linear regression. So you want to minimize the difference between whatever comes in and whatever function that you have. So whatever your data, difference between your data and some function that you calculate based on the positions of the atom. So our data is forces and positions, and we have a function that, given the positions, calculate the forces. We are minimizing this. This is a highly nonlinear. So instead of doing a linear regression or or any other linear regression, we do a highly nonlinear regression. But the idea is very, very, very similar. And then we find out a way to do gradient descent to actually find the minimum loss function. Okay, so our method, there are various methods to do this. Our method of choice is to use a neural network. Now, you could use different methods, but the idea of a neural network is that you have some input information that goes into what we call the input layer. Now, the input layer has these beads, which we call neurons. So there's an operation that goes on inside this neuron. Now, there's an output from this neuron that goes into another set of neurons, into another layer. And you go on like this for various layers, and it's a choice how many layers you have and how many of these neurons you have. And so you define a neural network based on the number of neurons on each layer and the number of layers that you're going to have. If you have more than just two layers, so an input layer and an output layer, then this is called a deep neural network. So you have these hidden layers inside, which is creates a deep neural network. And then obviously you can define how many connections you have. So sometimes you don't actually need all the neurons to be connected. But in our case, we use a fully connected neural network. So all the beads from one layer are connected to the next beads on the next layer, and so on and so forth. So now, what are we doing, really? So in actual fact, what are the calculations? So in essence, what you do is you want to train a neuron by calculating parameters on this neural network. And what are the parameters? So you have an input initially into each neuron, a set of input informations into these. and then you do a calculation. You know, here you have the value that is and there's no neuron turn on, so essentially the signal output signal is zero. Now so then the parameters are the input weights coming in from the various previous beats, and the various weights then go in linearly into this function, and then the neuron is either fired or not fired. And because you have, firing, and it goes on for the next neuron and so on and so forth. So it seems that the problem is linear, but this function is actually heavy here. So the function actually, so if you want to do, on and off, then the basic idea that you would have is to have a, a step function. However, a step function has a discontinuity, and if we want to do derivatives, then a discontinuity is not a good thing. Furthermore, typically a step function would give you overfitting. So imagine that
Alexandre, sorry. Yes. Alexandre, sorry. Your screen is not showing.
Okay, sorry.
Yeah, something happened.
Yeah. So where did you miss? So is it showing now?
Not for me. Not yet.
Let me share again. Apparently.
Yeah, and we had a little bit of problem with the sound too.
Okay. Let me know. Okay.
So now I see your screen sharing.
Okay.
Your main screen.
So where did you miss?
When you.
I think it was about 2 slides.
Yeah.
This one.
We are not seeing it.
We are not seeing it yet.
Oh. Let me see again.
It's better when you share the whole screen.
Yeah, that's what I was doing, but it's not working. How about now?
That's okay. Okay, you were explaining this slides.
Okay.
Can you go to the next one? I can see if it was
this one.
Yeah. What was at the beginning of that one that your sound got kind of shaky?
Okay. So the whole idea is that you have an input signal into a neuron, and this input signal actually comes from the set of previous neurons. So you have a number of input signals into this neuron, and this neuron will either fire or not fire depending on the combination of signals that are coming in, right? So this is a whole neuromorphic type of idea where you have a series of neurons that are connected, and then you have a circuit forming that will either, depending on combinations of neurons that are firing from the previous one, will fire on the next one. And so the weights coming from the previous neurons will go in together with the signal into this function, and then you have an output. Now, the whole idea of this neuron that then is depending on the value of the signal that is coming in, you have either 0 or 1. So this is the simplest idea, is that you either fire or not fire your neuron. Now, the problem with using a function that is a step function is that the derivative of the step function is actually it's a delta function, and this is usually mathematics or computer science is not very easy to simulate. So using a smoother kind of transition is typically better, and in particular, you also want your function to kind of favor or disfavor overfitting, which means that if you have a value of the argument of the function that is very, very large, then it will give you 1, and then if it's small, it will also give you 1. So you have a variety of possibilities for the same argument, giving you the same value for the function. So you try to avoid this. In our case, what we do is we use a kind of Fermi distribution together with a linear function. So then the values will tend to diverge as you go to infinity, and this actually brings down the weights to smaller values and avoids overfitting. Okay, now the other interesting thing about machine learning, in particular neural networks, is that there's a theorem which says that what you're trying to do then is to minimize this loss function. Now, basically, what this universal approximation theorem says is that if you have a function, in our case, then we're trying to minimize this loss function, which is basically the potential energy surface, or the difference between whatever you have coming in from the output, and you can actually approximate this any function, well-behaved function, so it continues by a neural network. And in physics, and in particular, in the dynamics of atoms, this is true, right? Unless you go for a very exotic system, then this is probably true. So basically, we're guaranteed that our problem can be solved by a neural network. Now, in the same way that when you're doing density functional theory, there's a theorem, so there is a functional, but you don't know what the functional is. There is no recipe to know what is the exact neural network that will describe your problem. So we need to find a good enough neural network, but we don't know what the neural network is. And worse still, there's no real prescription on how to get a very good neural network, right? So it's a trial and error. And then when I said we forego a model, right, because essentially here we set up the neural network, we don't have to worry about, essentially the physics, the underlying physics that is actually getting us the dynamics of the system. However, that's not entirely true. There is a model, and the model is the topology of the neural network. So given a certain topology, which means the number of neurons in each layer, the number of layers, how they are connected, then this is a model. And so we need to kind of come up with a model ourselves, and this is a little bit of try and error. There's no really way to go about this. But once you have a neural network, then you can go on to solve interesting problems. And the problem we're interested in is to solve dynamics of water and ice as well, which is a solid crystalline form of water. And then the group of Roberto Carr in Princeton, they developed this method based on neural networks where you can actually do get the potential energy surface of a system consisting of different sets of atoms. And one important thing about doing this is that if we're setting up a problem where we want to construct a neural network, we have also to consider the fact that if you take two molecules and you do a translation of these molecules, or you do a rotation of two molecules at the same time, then obviously the relative positions of the molecules do not change. So you have to go to a relative position coordinate system. But so these are what we call our descriptors. But once we do that, then we can actually go on and do simulations. So the point here is that we want to train a neural network to learn. So the neural network wants to learn about the forces on a certain configuration of atoms, and then we want to evolve this system for a large system in a long period of time to try to understand the properties of bulk water, which, as I'll show you, there still need a lot of information that are not known even today from a theoretical perspective. Now, the point of every machine learning model or any machine learning method, the quality of your data set. You know, sample the space. Basically, what we would be doing is an of this phase space, right? But we can't do that. We have to sample a part of the phase space and then try to fit a potential for that particular from that information. So we need to have good sampling. So this is the first part of how to train a neural network. We sample, and what we do in our case is we do initially we take a box of water, take water molecules and move around. All we need is water molecules, and we simulate of just things are a little bit more right. Don't want to be
Alexandre, sorry.
Not really much.
Sorry. Alexandre, your sound is breaking again. Sorry, your sound is breaking again. I don't know what the problem is.
Yeah,
so right at the beginning of this slide. Right at the beginning
of
this slide. Okay.
I'll try again.
Okay. I'm not sure what the problem is. It was okay for 2-3 slides and then it started.
Okay. Can you hear me now? Can you see the slides?
Yeah, it's okay. Yeah, and the slides they are not playing. They are in the they are not in the presentation mode yet.
Oh, okay. So
okay.
there's something wrong.
Yeah. No, now it's showing.
Okay. Let me see.
At the point you stop. Yeah. Okay.
Okay. So basically, the idea is that we take a small box of water molecules. We do classical simulations. We sample this classical simulation with a few different temperatures, a few different pressure configurations, so that you can have molecules which are slightly further apart. They're moving more or less, so that and these molecules are actually flexible as well, which is not usually what people do in classical simulations for water. And then because it's classical and it's a small system, we can do a huge number of calculations. Now we extract configurations which are not correlated, so configurations which are very different from each other, and we extract about 18,000 configurations. Now from these 18,000 configurations, then what we want to do is we want to train our neural network based on density functional theory. So we want to test different exchange of correlation functionals. So we do what is typically a GGA, which is PBE. Then we do a functional where you include van der Waals interactions. So GGA does not have van der Waals interactions. And then we do what we call a meta GGA, which is one step further on that Jacob's ladder. So we include the Laplacian of the density, and also the correlated part of the kinetic energy. And we take these snapshots and we run one density functional calculation for each snapshot. So we do essentially 72,000 calculations. So for each one of these exchange correlation potentials, we do the 18,000. So all the configurations are used again for each one of these data sets. And so these are our data sets. We have, so for each exchange correlation functional, we have a set of data sets, which is the forces on each of the atoms and the total energy of the system. So then we do the training. So we go to our training, we set up a neural network which has 4 layers. So the input, the output, and 2 inner layers. The first layer has 320 neurons, the second one 160, the third one 32, and the last one 16. So we learn from trial and error that going from a larger layer to a smaller layer at the end is actually better. And then we force and this sets up that given, the amount of frames we have, the number of force coordinates, and the number of molecules that we have, the number of atoms that we have, then the ratio between the amount of data points that we have to the number of parameters that our neural network is going to have is about 30, right? So we have, about 300,000 points of data for each one of our calculations. And then we do the training. So now the training is we do this kind of a self-consistent cycle where we go forwards and backwards. So we know what the forces are, and then we do a calculation on minimizing this loss function to get, the force, the difference between the forces calculated from our neural network and whatever you would actually get from calculating that structure on DFT. And then we do the simulation until the forces are smaller than 30 milli-electron volts per angstrom on each atom, and the total energies are smaller than 0.4 milli-electron volts per atom. So these are actually quite good simulations. And then once we have our neural network, then we use our neural network to do a molecular dynamics simulation. So we put structures in, get the forces, evolve the positions of the atoms based on those forces, get the new structures put into our neural network, calculate the new forces, and then we can evolve our system in time. And this is essentially what we do for these calculations. Now we train our neural network, so this is a typical graph for these kind of systems. We see that the neural network is well trained, that the errors are small, the distributions of the errors are small. And then we analyze, depending on the exchange correlation functional, the error on the density, depending on the number of molecules. So we do a small box with our neural network, but then we can do actually very large boxes as well. We see that the density doesn't change very much, and we get very good densities if we include the van der Waals correction, or if we include the Laplacian of the density in scan. So the values for the density are actually reasonably okay. One quantity that we typically calculate is the radial distribution function. So the radial distribution function essentially means you're calculating, you sit on an atom, say for example oxygen, and you look around that environment and calculate along the distance. If you find an atom, what is the typical distance between an oxygen atom and the first nearest neighbor, the second nearest neighbor, and so on and so forth. And you do this for each atom on your system for any given time. And so you come up with these, what we call these radial distribution functions. So it's an average of the density of the oxygen atoms from a distance from an oxygen atom. And we see that there's not big changes coming from the structure, so the number of atoms. So increasing the number of atoms is not something that changes drastically. So this means that if you're calculating these RDFs, which are extremely important for structuring, doing neural networks or doing DFT is not really much of a big difference. And if you change the exchange correlation potential, provided you have go away from GGA, which is usually very bad, it leads to structuring, then you improve. But you're not really much better in terms of comparing to experiments. So the experimental values here are the dashed gray lines that you see on the graphs. And if you look at the oxygen-oxygen, then there's a small change. But in the oxygen-hydrogen distance, then that is really bad compared to the experimental results, especially the first peak. Now, what is the origin of this? We'll see in the next slide, but another thing that we want to calculate is the diffusion coefficient. So it's how a single water molecule diffuses inside water. And you can see that the diffusion coefficient, so the dashed line there is actually the experimental result. And you can see that it's actually pretty bad compared to experiments. So by a factor of, I don't know, for GGA, by a factor of almost 10. For the other ones, by a factor of 3 or 4. So I mean, the comparison is really bad with experiment, meaning that the diffusion of water is actually very poorly described within our neural network and within density functional theory in general. And what is the reason for this? The reason for this is because of nuclear quantum effects. So the problem is that, you know, the hydrogen atom is not well described by just doing a point charge. You need to include these effects. We include them by using what we call path integral molecular dynamics. And so when we do this, and this is including this path integral molecular dynamics method, so you actually get a very good agreement between the radial distribution functions and the experimental results, right? Especially for these exchange correlation functionals, which include the van der Waals interaction. And this is true for the oxygen-oxygen. This is particularly true for oxygen-hydrogen and the hydrogen-hydrogen as well. And then when we do a calculation for the diffusion of coefficient of water, then we find that the diffusion coefficient of water actually improves considerably compared to the case where you didn't have nuclear quantum effects. And they actually become quite close to experiment, particularly with this exchange correlation function called van der Waals CX, and also SCAN. So both of them are actually in very good agreement. Not only the diffusion coefficient, but the slope of the line is the viscosity, which is also in very good agreement with the experiments. So the inclusion of these nuclear quantum effects is extremely important. Now, how do we actually model this? And so this is something that is extremely important, is that what is the effect of the time scale of the simulation and the size of the simulation? So the dashed line is for a small size, the solid line is for a system containing about 2,000 molecules. And so we see that, first of all, if you take a small system, the diffusion coefficient never converges, or at least not for 2002 nanoseconds. But whenever we do a large system and we do a long simulation, then we clearly see that things start to converge after about 1 nanosecond. Everything is more or less converged for all the potentials that we have simulated here. Right. So the message that I want you to convey here is that we wouldn't be able to simulate these diffusion coefficients, which are relatable to experiments, unless we were doing a calculation using these neural networks, because it's impossible to do a calculation like this using just density functional theory with a large system. So it would take hundreds of years to do this, whereas we can get these results, one of these curves, by after a week of simulations on a 16 node computer. Okay, now the other question that we can ask, and this is an extremely important question because we need to set up a data set, so we need to do a lot of DFT calculations. So this is my last kind of message. What we did was we went back to our system and we took different sizes of our data set. So we do, instead of taking 18,000 frames, we took only about 10%, then 20%, so on and so forth, up to about 100 of the total of 100%. And we calculated the errors on the energies and the forces. So we trained a different neural network for these different data sets. And so this is an important thing. And then we calculate what are the radial distribution functions for these systems. And we find that if we are only looking for structural properties, then everything seems very good, even with 10% of our data set. So with only about 2,000 frames, if we select these frames in the same way that we did, right? So we take randomly out of those 18,000, only about 2,000. Then the errors on the Reily distribution functions are relatively small, so less than 1%. So we can get, very good structural properties. However, when we look at the diffusion, then things are a little bit more complicated. So we see that with 10%, the diffusion is actually, not very good. But by the time we reach about 50 to 60%, the diffusion, we already get a very good description of the diffusion coefficients. So we can actually reduce our data set by about 50%, and this is already a very good size for the data set. So this is an important point because it means that you can, get away with this with a smaller data set. However, I'm not going to show it here, but so what we do in that sampling, so we do this random sampling. Now, typically what people do is different. What people do is they select, they had it done in the past, a long density functional theory calculation, maybe with 30,000 time steps. And we use, then since they already have this data set, then they take the entire data set and do the calculation. Now, we also did this. So we did a small calculation with the same size, only 2,000 points, 10% of our data set, and then tried to do a simulation. And then because everything is very correlated, then things break apart. So the message is we do a very good sampling, and our very good sampling actually allows us to reduce the size of the data set to a smaller size. So so I'm about to finish. So basically what I wanted to convey to you today is that, we can do simulations of aqueous environments with very large systems and very long time scales. We can do this using, neural networks. We can provide a kind of a recipe to obtain very good results comparable to experiments for various properties of water. And this basically needs the inclusion of all the ingredients. We need to have a good exchange correlation function. We need to include nuclear quantum effects, and we have to have good sampling to have a good neural network. So with this, I'll thank you for your attendance. I'll acknowledge the people who have been working on this project with me, and I thank you for your attention.
Thank you, Alexandre, for this very didactic talk. So we are open to questions now. Anyone? I see that Gerson has a question.
Yeah.
Who else? Gerson, go ahead.
Okay, so first, thanks, Alexandre, for a very nice talk. I've been playing around with neural networks just for fun, very simple problems. And I've been following the DFT approach for neural networks, reading the papers, and everything is quite amazing, quite interesting. I didn't know about this kind of approach for molecular dynamics, so I'm glad to see it here. I have two questions. One, you said you were using this for the activation function x times hyperbolic tangents, and I understand.
No, the distribution. So so x plus the Fermi distribution.
Okay, but it's more or less the same thing. You're avoiding the plateau in a way.
Mm-hmm.
So this makes a huge difference for the convergence. How much does if you put the Fermi distribution, what changes?
Yeah, it's not so much the convergence. What we find is that this avoids overfitting. So the problem is that because if you only put a inverse tangent or a Fermi distribution, what you get is that you get a whole range of parameters or a whole range of arguments to your function that can give you the same signal essentially, right? So put in an x value, then the value of the function will be much less dependent on the argument. Or it will be much more dependent on the argument. So this avoids overfitting. There's not so much the convergence. The convergence they always converge.
But in practice, what changes between the results? What's
you get the errors when you compare the errors. So when you do the testing. So yeah, something that I didn't say. So typically, I know you know, but I mean just to explain people. So typically, what we do is you take your whole data set, you select 10%, 15% of your data set, you remove it and hide it from the neural network. So you take 90%, you train with that 90%, which the neural network knows about, and then when it's trained, you get those 10%, and you see if the neural network actually gets very good results for those 10%. So basically saying, okay, if you're exposed to something you haven't seen, whether you give good results, if it is a good fitting in there. And the answer is that fitting, so that testing improves if you do this.
I see.
For this particular problem.
And why not using the hyperbolic tangent to avoid the plateau of negative values?
So the hyperbolic tangent
to avoid the plateau for negative x, because
so the hyperbolic tangent also will give you will go to a constant at the end.
No, see, I mean x times the hyperbolic tangent.
It could be. I mean, it's at the end. I mean, we didn't test that widely. What we did was a function that will be differentiable and will have this kind of a slope. Then could be anything. It doesn't really matter. I mean, then it's a little bit like fine tuning, and then this is a kind of a black magic. You test and see which one is better.
That's my current problem.
Yeah, I mean, this is the one. This is the big problem with this is that, I mean, you test a huge number, you kind of get a feeling that this is working, but there's no really kind of a physical intuition. Yeah, there's no systematic approach.
So this actually answers my next question. How do you choose the size of the network?
It's just you set it up, you run a few different configurations and see which one is the best.
At some point, you were showing that the ratio between the number of data points and the number of parameters is about 30. So having this ratio much larger than 1 is important. What is the significance of this number?
Yeah, so the ratio larger than 1 means, because if you have 1, basically what you're doing is interpolating, right?
Yes.
Then if you have less than 1, means that you basically have an indeterminate system, and then so we found that 30 is a good, between 8 and 30 is okay.
So this gives you a guideline to choose the size of the network, but then you can change the number of layers and the number of neurons, and this is kind of a broad thing to ask.
Yeah, so the thing I didn't say, but it's when we reduce the size of the data set, we kept that number fixed, so we reduced the size of the network that is trained as well. So the network is smaller than the previous one.
Yeah. Okay, perfect. Okay, thanks, Alexandre. It was quite nice. Thank you.
I have a couple of questions. Actually, if no one has a question, it doesn't seem nobody raised his or her hand. By the way, I like your picture. Oh, there is Liliana. Liliana, go ahead. She's.
Hi. Let me see if I have. Oh, it will be. Let me see if I have camera or not. But it's just a curiosity. What's the problem with the classical methods exactly? Because you show a very nice slide. Can you put that? Can you put it?
The slide with the potential.
Yes. It's not potential. It's the second one after the potential.
This one.
When you explain all these, this one. So you put all these ingredients, and that's quite interesting. So what is the problem with that?
Yeah, because there's no guarantee that the actual potential will be in this form, right? I mean, what we're doing is, for example, there's no guarantee that the bonding interaction is a spring, right? Is a k squared, x squared type of potential. So in a sense, you're trying to model a problem with some physical intuition. It works very well for various systems, especially organic systems. It works very, very well. But it's a model that is not. I mean, it's still fitted, right? So you need to fit these parameters, and what usually people do is they either fit to a simpler density functional theory calculation or or a class experimental result.
Okay.
So, but this is another thing, right? What you could do, not with neural networks, but what you could do is you can do you use some form of regression to fit parameters for these type of models. So this is something that people are doing, right? So they do a calculation, small calculation using DFT, and then you set up the model, and then you try to minimize this model based on
like
the DFT.
variational calculations.
Yeah, exactly. And so this can be done.
But it's really nice.
That is, yeah. For me, is the biggest problem is that there's no transfer.
The sound is not good.
Your sound is breaking.
No, and now he disappears.
Yeah.
And now the presentation.
Everything disappeared.
Can you hear me?
Now, yes.
We can hear you.
Yeah, but we don't see you.
Yeah, try to. Seems. Okay.
But okay,
Yeah,
it's really nice to see you again, Alexandre.
Yeah, nice to see you as well. Okay. Hopefully next time I'll be physically there.
Yeah, come in the winter. Come in the winter. I have just a question and a comment. You mentioned about this effect that you have to take the proton in account in a more sophisticated way. I assume that for heavy water, this would be even more so. Is that true? Or the neutron doesn't?
No, it's the other way around, right? So the heavier the atom, the less
easier it is. Okay.
Yeah. But it's still important. So essentially, this effect people will take into consideration when using hydrogen, deuterium, and lithium as well.
Okay.
This is typically what people have to do. Yeah.
For this 3-1. Okay.
Yeah.
So another thing I got, I think that was one of your messages, that a lot of calculations that with pure DFT, the traditional way, were impossible to do. Now using machine learning, they became possible. I recall, I don't know if you know David Tomanek from Michigan State University. I have been to a few of his seminars, and I recall that he showed a calculation he did, which was way less calculations that you are doing there, and that he needed to use at the time was the fastest computer in the world in Japan, to do a calculation that was just to know if a hydrogen was going to bond or not bond to a molecule. And it took him weeks in the fastest computer in the world. So it's really an improvement using neural networks, I assume. Okay.
Yeah. I mean, for example, this program that we're using, actually now it's on GPUs. So we do all the calculations on a single GPU, and it runs, in a week maybe. Everything is done. So yeah, it's a completely different ball game.
Okay. So good for us.
Yeah.
Okay. So any other questions? Anyone? So if not, let's.
I do have.
Edson. Yeah, go ahead.
Sorry,
go ahead.
So actually, just made all question I had. So most of them was already answered. So thank you for a nice talk. and for accepting the invitation.
Thank you.
There is one last question. So if you want to, I think it was a nice idea to work without a model. So you don't have a model. So in principle, you have more general result, right? You're not bound to a model. So is there any chance to do calculation in unsupervised learning? So you don't have the data at the other day.
Yeah.
So that
it's a good question. Because typically what you do in the unsupervised learning is you do more like categorization or reduction of the space, clustering, so you find similarities between systems. I have to think, but I'd say it's more difficult to do that in a sense. But because then basically if you do unsupervised learning, what the system would be doing is to learn the rules of quantum mechanics, basically, right?
Essentially, yeah, basically, yes. Yeah.
So
it should minimize some energy.
Yeah, I think if we teach the computer to learn the rules of quantum mechanics, that would be quite something. But I'm not sure if yeah.
Very good.
Although, I mean, I know that there are some people that have been working on this. So they have been working on, getting the computer to learn the laws of physics. And apparently the computer has already come up with, Newton's second law. And I think even, I don't know what other things, but I mean, some simple in a sense, right? But I mean, I don't know what kind of information it provides, but it has been able to.
Because usually unsupervised learning, you have the Hamiltonian, so you have a model, so you have unsupervised result.
Yeah.
Now, I think it's stretching too much, removing the Hamiltonian and the data. So Okay, thank you.
Yeah.
Okay, any more questions, anyone? So if not, we should thank the speaker again. Thank you very much for the nice talk, and thank you for accepting the invitation.
It was a pleasure.
And I forgot to ask, I always forget. We recorded your talk, and we intend to post it in our YouTube channel. Is that okay with you?
No problem at all.
No problem. I will ask for the slides too. I will send you an email.
Okay.
If you,
I'll export them to PDF and send them to you.
Okay, no problem. Okay, thank you so much.
All right, thank you. It was a pleasure.
Okay.
See you guys.
Bye-bye. See you.
Bye.